Look at our groundwater flow problem. So here we're going to solve the equation where the gradient squared of h is equal to 0. In other words, the gradient in the head in both spatial directions is 0, the Laplace equation. Okay, so if you remember, we went out to site and we explored a rectangular piece of ground, and we discovered at the northern section we had a value in h of 100. So we can set up a Dirichlet boundary condition here. And I'm going to do that for a few grid cells. Okay, and on the western side of our boundary, we also measured a value of 75. Okay, and let's just increase this to 9 for now. All right, and on the the eastern side of our boundary, we measured a piezometric head of 50. Okay, and then if you recall, we also did some measurements at the southern end of our site, and we discovered that there was no flux across this boundary. So that means we have a Neumann boundary at the southern end and Dirichlet boundaries around the site. Okay, so that's going to have some implications later on, but let's see how we can use Excel to solve this partial differential equation. So first off, I'm going to use Liebman's method, or the Gauss-Seidel method, and that is equal to the sum of the grid cells around the node of interest, all divided by 4. Okay, and I'm going to click and I'm going to drag this across. Now I'm going to leave it like that for now. So let's just check everything's okay. Okay, and now we're at the Neumann boundary. Now if you remember, at the Neumann boundary, here we've specified no flux, so the gradient is 0. And that has a special implication for our Laplace operator. So the value of the Laplace operator is equal to 2 times the node above, so 2 times the node above, because we are specifying the flux in the y direction as being 0, plus the nodes on either side, all divided by 4. Okay, let's just check here. Okay, so at the moment we don't have, doesn't appear to be solving anything. And if you look at the bottom here on our screen, you can see a circular reference warning. So there's an issue with our Excel. Well, I can change that by setting up my calculations iteratively. So in a Mac, if you go to Excel and Preferences, I can go to Calculation and use Iterative Calculation. Let's close that. And then for a Windows machine, I believe it is under File, Formulas, or I think if you can just go to Formulas and Calculation Options. All right, so now I've done some calculations. And I'm just going to hit the function F9 key just to make sure that the solutions are converging. In other words, they don't change very much. Okay, which appears to be the case. And now let's plot our data just to view it. So let's insert a chart, and I'm going to insert a 3D surface. We don't want a wireframe, we want a 3D surface. I have to select my data, so I'm just going to put the midpoint here. So that's equal to 100 plus 75 divided by 2, and this is equal to 100 plus 50 all divided by 2. Let's close our brackets off. All right, so now let's select everything and plot it. Okay. So it doesn't really look like much. I'm going to just make this plot a bit bigger so we can see it. And I'm going to rotate it around. So let's go to Format, 3D Rotation, and let's see what happens. Now we don't want to go Y in that direction. Let us rotate the X in this rotation. And there's something else that I want to do. I want to change my layout because I'm not, you can see that the 100 value is on the side here and it looks a bit different to how I've got it on my screen. So let's go to the vertical. No, I don't want to go there. I want to select data and no, I don't want to go there. I want to flip my X and Y. So no, let's go to axes options. Okay, somewhere here I should be able to change the okay, so that's a bit better. But it's still not quite how I want it. So let's just click on our graph and let's click on the rotation and let's rotate the X a bit more. Okay. So this kind of makes a bit more sense. So we've got the value 100 at the top here and the water is flowing down towards draining in this direction. Okay, that's pretty interesting. But let's try and refine our grids. In other words, we need to add more grid cells. So I'm just going to add a bunch more grid cells here. And you're going to see why I'm going to do this in a minute. And let's copy this last value, our no flux boundary condition. And let's copy the formula in this direction. And hit function F9. Now remember, the size of our domain has not changed, but because we're using more elements, we've refined the grid. Okay, so let's just select our data, just extend it here. All right, so now we've got a nice looking plot. But let's say I come along and I put my piezometer somewhere on the side. So now we can look at so what we're viewing here is we've measured the piezometric head around the boundary of our site, and we've assuming that there's a no flux in the Y direction. So I now come along and I insert my piezometer somewhere here and I measure that the height is actually, instead of 69, well, let's go to 66, it is 80. All right, let's increase this a bit more. 100. Okay, so what that means is that I now have to recalculate the or solve the partial differential equation, which is going to change my flow lines or lines of constant h. And then let's say I measure somewhere down here that instead of 61, it's actually 40. Okay, so we've got a sink term here. Now you can see how it's changed the flow, the lines of constant h, the iso lines, whoops, and I'm just going to hit function F9 just to make sure. And what I'm also going to do is change the, so let's go to our y-axis, and what I want to do is change the number of contours. So to do that, if I go to chart design, format, let's go vertical axes, and let's change our unit to 10. See that we have plotted now many more isolines. So let's, if we change that to 5, you can get a better idea of what's happening. And so we can see how for a rectangular grid, Excel is pretty good at showing us visually quite quickly using an iterative method how the solution in the spatial domain of our partial differential equation looks.